Hey everyone, how are you? Um, so we are going to focus on the solar system now. We have studied the galaxy, the creation of the universe, stars, the Milky Way galaxy. We're gonna bring it in. So the way that we study astronomy is we start big, and then we bring it into the galaxy, and then we bring it into our solar system, and then what we're gonna do right after this is we're gonna bring it into the sun, Earth, and Moon system, so that we can start studying eclipses and lunar phases and things like that. But normally, if you look at the PowerPoint, which I have uploaded, by the way, to Teams files. So if you go into Teams and files, this entire PowerPoint is there. Normally, we would spend some time studying a little bit about the sun, and you can look at that in the PowerPoint. It's fine, and you can kind of check out sunspots and how they're cyclical and things like that, but it's a little dry. So we're going to focus on the planets and the shapes of their orbits. We're not going to really like study the planets in detail, like what is the surface of Mars made of and things like that. What we basically want to do is we just want to know kind of generalizations about the planets, and the way that we do that is by looking at the ESRT page 15. So we've already taken a look at this, the HR diagram, which shows you where stars are located based on their luminosity and their temperatures. But this chart down here is basically everything you want to know about all the planets. Okay, so I just wanted to go through it a little. Stuff you don't have to memorize, right? Okay, so we have the sun, the 8 planets. Pluto was booted. We'll talk about that. All right, and the Earth's moon. And notice the second column here is mean distance from the sun. Not distance from the sun, mean distance from the sun. That tells you something. That tells you that, hey, you know what? If it's a mean or average distance, the distance between the planet and the sun must not always be the same. Okay, we're going to talk about that. All right, the third column here is period of revolution. Well, like in hockey, each period is 20 minutes long. So a period is an amount of time. Like a periodical is like a magazine. It comes out a certain amount of time it comes out every certain amount of time. So the period of revolution is the time it takes the planet to go around the sun. Period of revolution. Period of rotation at the equator. Okay, the period of rotation at the equator is how long it takes the planet to rotate on its axis once. So there's something very interesting here. If you look at Venus's data, Venus's day is longer than its year. Whoa, that is weird. Okay. And note that everything is in Earth days and Earth years. So that's our standard of time, an Earth day and an Earth year. So all of these measurements are in Earth days and years. Okay. And something that we're going to focus on today, this is what we want to take away from today: the eccentricity of the planet's orbit. Basically, if you were to go out into space and above the sun's north pole and you look down on the planets and the planets made a trail as they were orbiting the sun, if you looked at that trail with the naked eye, if you looked at the shape of the planet's orbit with the naked eye, it would look to you like it was a perfect circle. But none of the planets have a perfectly circular orbit. They're a different geometric shape called an ellipse. And the measure of how elliptical their orbit is called the eccentricity. Okay. And eccentricity is actually the last formula in your ESRT. Okay. The eccentricity of a planet's orbit is found by measuring the distance between the foci, and you're going to learn what those are in a few minutes, and dividing that by the length of the major axis. Okay, so that's the eccentricity. All right. So the higher the number, the higher the value of eccentricity, the more eccentric, the more elliptical the shape is. So you can think of an ellipse as an oval, kind of. Okay. You have a perfect circle, and the more stretched out it gets, the more elliptical or more eccentric it gets. Okay. So that's eccentricity of the orbit there. And if you look here, which planet is the most elliptical? Which planet is the most eccentric? Right? Who is the highest value here? Okay. Mercury. Mercury is the most eccentric or most elliptical. Which planet's orbit is closest to being a perfect circle? Which planet's orbit is just slightly eccentric? With the lowest value? Yep. Right there, right? Venus, right? So Venus is the most like a perfect circle, and Mercury is the most like an oval. Okay, so, but none of the planets are perfect circles. Okay, and that was hard to figure out for astronomers. All right, and then we have the equatorial diameters, and it says equatorial diameter because what do we know about the Earth? Where is it fatter? At the equator. So it's not the polar diameter, it's the equatorial diameter. And then you have the mass relative to Earth. So Earth would be 1. Any value that's lower than 1, less than 1, is less massive than Earth. And any value that's greater than 1 is more massive than Earth. And so we have the teeny tiny, puny little terrestrial planets, the inner planets, and we have the ginormous outer planets, and then we have the moon. Okay, look how much more massive the sun is than the Earth. The sun is huge. Okay, and then finally we have the densities of all the planets in the sun. Which planet, if you had a bathtub big enough full of water, would float? Right there. Who would float? That'd be Saturn. Okay. So this table here allows you to look up any important data about the planets that you need. Okay. And that's page 15 of your ESRTs. And so, how do I get myself out of here? Oh, wait. Oh, there we go. Oh, wait. Oh, I'm going to make myself small. Okay. So, what I'm going to show you is just some pretty pictures of the planets in the solar system. We're going to go through these pretty quickly. Okay, the inner planets are terrestrial, they're denser. There's the inner planets. Okay, there's Mercury. These are actual photos. There's Venus. Okay, Venus is the greenhouse effect on steroids. What gas do you think Venus's atmosphere is primarily composed of? Well, if it's the greenhouse effect on steroids, carbon dioxide. Hometown feeling, there's Earth. There's Mars. Mars does have an ice cap at the southern pole. Okay, there's a really big canyon on Mars called the Valles Marineris. Okay, that's an actual photo of the surface of Mars taken by one of the Mars rovers. We'll talk a little bit about Goldilocks planets another time. Okay, the outer planets are the Jovian planets. They're the gas giants. There's Jupiter. Beautiful, isn't it? And Jupiter has a whole bunch of moons. Right, these are the 4 big ones, the Galilean moons, Io, Europa, Ganymede, and Callisto. There's Saturn. Gotta love Saturn's rings. Okay, and Saturn also has a lot of moons. The larger planets have more moons because they have a greater gravitational pull because of their mass, and they attracted more objects in the solar system when it was forming. There's Uranus, or Uranus, ha ha ha, it's funny. Okay. Uranus does have a ring system, but it's vertical, not horizontal. So it's like perpendicular to the plane of its orbit. All right, that's pretty cool. And Uranus does have moons. Uranus is blue. Uranus has rings, ha ha ha. Uranus is a gas giant, ha ha ha. Okay, Neptune. Neptune has also 13 moons. And Neptune is a beautiful blue color. And Pluto was booted in 2006. It's now considered a dwarf planet because Pluto did not meet the new definition of a planet that they created. Okay, so Pluto is a relatively it is in orbit around the sun. Okay, that's requirement number 1. It does have sufficient mass for its self-gravity to overcome rigid body forces so that it assumes a hydrostatic equilibrium or nearly round shape. So is Pluto spherical? Yes, that's that big sentence there. And C, has the planet cleared the neighborhood around its orbit? So in other words, the planet's orbit doesn't cross another planet's orbit. This is where Pluto doesn't make the cut because Pluto's orbit crosses Neptune's orbit. No, they're never going to crash into each other. Okay. So Pluto, because it's more elliptical, crosses Neptune's planetal path. That's why Pluto became a dwarf planet, because it crossed the Neptune's planetal path, orbital path, excuse me. Recently, they sent a probe to Pluto, a flyby, and it got some really, really good photos of Pluto. Pluto does have a major moon called Charon, and then Hydra and Nix are smaller moons. Okay. And here are all the moons of the solar system. And this is Earth, so you can see their relative size to Earth. And our moon, Earth's moon, is a pretty substantial moon. I mean, Jupiter and Saturn have larger moons, but we have a pretty good sized moon. And basically, everything you ever wanted to know about the planets, like I said before, is on this chart. Okay. There's other small bodies in the solar system. We'll talk about them another time. Okay. What you're going to do now is you're going to watch a few videos that take you through. Hold on. It takes you through Kepler's laws. Okay, so Kepler's 3 laws of planetary motion, it explains them for you. And Kepler's laws are what we know about the shapes of the orbits. All right, and this is pretty important. Okay, so it's a measure of eccentricity, and this is how you calculate eccentricity. It's very easy to do. And the videos just take you through what Kepler's laws are and how he figured them out. It was kind of like a little bit of a soap opera type thing, where one astronomer really tried to mess with another astronomer and didn't give him the data and whatnot. Okay, but it's very interesting. And so there's a few Edpuzzle videos that you're going to watch, and you do some work, and it's pretty short amounts of work today in the BFRB. Try to lighten things up for the weekend. Okay. So take care, everyone, and I'll talk to you soon. Bye.